Okay, so we're going to look a bit at solving geometric problems using vectors. We've done this before using 2D vectors, but now we're going to look at some problems with 3D vectors. I think the case with solving vector problems is that you only really get good at it by just practicing a variety of different problems. It's not the sort of thing where you can just explain the rules and then you're able to do it. So this is, unlike the previous two sessions where it's just a case of explaining rules and then that's it, you kind of get the rules. For solving the geometric problems, you just need to practice a few different types. So what we'll do is, I'll basically go through 4 different examples and I'll intersperse that with a couple of tips. So I'll give you a tip and a couple of examples, and then I'll give you another tip and a couple of examples, and then you can try some questions yourself. Okay, so the first tip I want to give you, it's about how if you're given a 3D scenario, so say you're given a series of points which are 3-dimensional, when it comes to sketching it, most of the time you don't really need to worry about sketching it in perfect 3D. It depends on the question, but a lot of the time it doesn't really matter. What matters is the relationship between the points. So let me give you a sort of arbitrary example. Let's say you're told I have an equilateral triangle. So I'll just make up a question. I have an equilateral triangle in 3D space. Then let's say I give you the points with points 1, 4, 2, 5, 4, 3, and these. Okay, so those two. I've got those 2 points, and if it's an equilateral triangle, then presumably there's a limit to what the third point can be, right? It's restricted. How would it be restricted? It's presumably restricted in a sort of, one dimension. Okay, so let's say, I'll make this up. Okay, it doesn't matter, you don't have to solve this question. Let's make that a 7 just in case. Okay, let's say something like this. All right, maybe it's solvable, maybe it isn't. But the point is, when it comes to sketching this, so the question is find AB. The point is, you don't have to worry about sketching it in perfect 3D. What you can probably do is just say, right, I've got 3 points. They're equilateral, so they have the same length. So you could at least sort of draw them with the same length, and then just label the points correspondingly in 2D. Okay. I mean, this might seem obvious, but for certain questions, especially when you start getting more points, this is what you really need to think about doing, because you can't just draw everything in 3D, because that's going to get too difficult. But what you can do is just plot the points on the 2D paper and then think about the relationship. So for example here, I've shown that that point's connected to that one, that one's connected to that, and that one's connected to that. They're all the same length. I mean, I'd have to write that somewhere. But I didn't have to draw it in 3D in order to illustrate that. So the sketch, the 2D sketch of the 3D scenario, although it can't show you, the precise arrangement, what it can show you is the relationship between points. Okay, so keep that in mind. I think the second example in particular will make use of that. Okay, so let's take a look at our first example of solving a geometrical problem. So let's see, we're given 4 points. We're asked to find the vector from A to B and the vector from point D to point C. Okay, let's do that first. So that's a little bit of pure calculation. Let's lay out the notation formally. So vector from A to B, that's going to be the B position vector, which is 1, -7, -3, minus the A position vector, which is 2 minus 5 minus 8. And I get minus 1, minus 2, 5. The DC vector is the C position vector minus the D position vector. And that's equal to minus 10 minus minus 20 minus 10. No, 10. Okay. Right. So we've done that. Give your answers in the form. Oh, God, you have to write it in that form. Okay. So then I'd say minus I minus 2j plus 5k. And in this case, minus 2i minus 4j plus 10k. Okay, now we're done. Now we need to show that the lines AB and DC are parallel and that DC equals 2AB. That's almost giving us two information, really. This equation saying DC equals 2AB, that effectively is proof it's parallel. If I show that one vector is the multiple of another, that's parallel. So basically it's just asking us to show that. Okay, just show this and then just declare it's parallel. And that's easy, isn't it? Because in fact, if you look at that vector there, multiply it by 2, you get the vector at the bottom. So pretty much all the work is done for you. You just need to say, you know, this times 2 gives me this, therefore this equation, and therefore they're parallel. Okay, and then for part C, we want to describe the quadrilateral ABCD. In other words, what kind of shape is it? So let's think about the information we've got here. So this is one of those cases where you don't need to, you know, don't start plotting these 4 points in 3D and then thinking about the shape. That's far too complicated. So what do we know? We know that AB and DC are parallel, and we know that DC is twice the length of AB. So let's draw that out briefly. In fact, let me just make a little bit more space here because I don't think we need this anymore. So if I just randomly draw a line, and I'm just going to declare that that line is AB. Then think about the possibilities for DC. In fact, let's do this the other way around, sorry, so that I'm doubling rather than halving. That's DC. AB is going to be double that length and parallel to it. So it's got to be parallel. So it can't do something like that. You know, it can't do something like this. And it's got to be twice the length, so it can't be small, you know, it can't be that long. You've got a certain amount of restriction. If you kind of envision all the possibilities, let's just put down one possibility. Say something that looks like about this. That's about double the length, I think, and it is parallel. Okay, that's one sort of possibility. And then if I chose that possibility, then what remains is to connect up the other points. If it's a quadrilateral, I can't connect things like this. That doesn't make sense. So the only possibility is to place the lines like this, connecting them. So therefore, once you've picked which AB line you're going to use, then the rest falls into place. Now in this particular instance, the AB line I picked gave me a particular quadrilateral, right? In this case, a trapezium. Now, all you have to think about really is, if I had picked this AB a bit differently, as long as it's still parallel to DC and double its length, am I still going to get a sort of trapezium shape? So in fact, wherever you put it, it will in fact still be a trapezium, right? It could be technically an obtuse trapezium, which remember is still a trapezium. So that would be the case where, say, let's say I picked AB so that it looked like that. Okay, as long as these two blue lines aren't parallel, then this is that's still a trapezium. That's a, not one that how you usually see it, but it is still a trapezium. Because the rule of a trapezium is simply that two of the sides are parallel, and not of the same length in this case. Because if they were of the same length, then obviously the two blue lines would be parallel. Okay, cool. So that's it. No need for a 3D sketch. A 2D one will do. Okay, so let's look at this one. You've got 4 coordinates and they form a parallelogram. P, Q, R and S, and you are given the values of P and Q. Find the coordinates of S. Okay. One thing that's important, very important, is that, like with 2D, the order of the points, by convention, they still have to cycle and connect in that order. So you're given information already by the fact that it's P, then Q, then R, then S. You have to connect them in that order. So if I do a P here, let's say that's P, that's Q, let's say that's R, and then S, because it's a parallelogram, let's draw it so it roughly looks like a parallelogram, S here. Okay. And then I'll connect up those points. And if I then just label these quickly, so this is 4 minus 9 minus 3. This one's 7 minus 7 minus 7. 8 minus 2, 0. And then S we don't know. We're not sure what S is, so we're going to have to think about that. What I should also do really is just label these sides to make it clear that they're parallel. So the direction of the arrows doesn't particularly matter there. I'm just declaring that the opposing sides are parallel. So the way we're going to do this is, let's think about 2 possible routes to get to the same place. Okay, and let's say from the origin. So remember, there's always a sort of invisible point out there which we call the actual origin, which is what we take all these things with reference to, right? Because say this 4 minus 9 minus 3, that's with reference to some point, right? It's saying start at the origin, go 4 along the x direction, minus line along y, minus 3 along z, and you'll get to P. Okay, so it's out there somewhere, this mystery O. And what we can say is, right, if I wanted to get to S from O, right, which is S's position vector, that's what I'm trying to find, how could I get there? Using stuff I know. So let's try, first of all, what if we go from O to P? Then I suppose we could go from P to Q, then Q to R, then R back down to S, and I'd get there. Bit complicated though. We can take a shortcut, because I know that PS, that vector, is exactly the same as this one, QR, because it's a parallelogram. Let's note that for a moment actually. PS and QR are the same thing. Okay. And also going from P to Q and then back from R to S, that's also just, repeating myself really. There's a quicker way we can do it. We can just say go from O to P. Let's write that down. Go from O to P. So that's from there to there, along this sort of, I haven't drawn it in, but there's a sort of invisible line here. Okay, that's O to P. And then let's go from P to S by adding the QR vector, which is the same thing as the PS vector. And that should be equal to the position vector OS, which is what we're trying to find. OS is equal to that plus this. And then OP we know, that's just 4 minus 9 minus 3. And QR, we just need to make a note of what that would be. QR is going to be the R vector minus the Q vector. Okay, so in 3D it's all about just using the rules of vectors, not worrying too much about what it actually looks like in 3D space. So it's a lot more theory based. 8 minus 7 is 1. minus 2 minus minus 7 is 5. I've written it poorly there, that's a 0. Minus minus 7 is 7. Okay, so I've got 1, I've got 5, I've got 7. And that's this value here, the QR. And the P is the 4 minus 9 minus 3. So I'm just going to make the origin invisible again for a moment. Let's move this across and let's finish it off. So we've got this is equal to 4 minus 9 minus 3 plus 157, and we get 5 minus 4, 4. And that's it. That's the coordinates of the point S, because that's its position vector. Remember, the coordinate is the same thing as its position vector, O origin to the point, which in this case is S. So OS is equal to that, 5 minus 4, 4. Okay, so one more, I suppose, tip or rule before I'll do a couple more examples. The idea of comparing two 3D vectors, or I suppose two linear combinations of vectors. Okay, when can I do it, when can't I? You can do it most of the time. So let's say I told you I've got the following vector, 5i plus 3j plus 2k, and I said it's the same as another vector I've got, which is 5i plus 3j plus some unknown, let's call it little a, k. This seems unbelievably obvious. What's the value of a? It's going to be 2. But remember that technically speaking, what this is all doing, it's not saying I is not like some type of thing I have. It's not like I've got 5 i's and 3 j's and 2 k's and never they can combine. I, j and k are just vectors. So sometimes two different vectors could add up to become the third vector. Like what if the i's and j's could combine to make some multiple of k? So the only reason they can't is because of a fact that we know about I, j and k, which is that they are non-coplanar. So what this effectively means is that they don't all lie in the same plane. Okay, so maybe we can convert this a bit to the 2D case. Okay, let's think about 2D for a moment. In 2D, you're going to just sort of have to follow, what I draw as I say. If I have a vector, if I draw a random vector, okay, and then that defines a line. And in 2D, I can only compare combinations of vectors if they're non-linear. So if I draw another vector, say this one, oops, that's in the same line. So I can't compare combinations of them. So for example, if I said I'm going to define that as my I and that as my j, that's useless, because multiples of I and multiples of j could end up being the same thing. However, if I have them non-linear, for example this, or even if they were perpendicular, even better, then it's fine. So to compare coefficient, or to compare linear combinations, how should I phrase this? Let's say compare the coefficients of linear combinations. So by the coefficients, I'm talking about the number just in front of the vector. For example, for 5i, it's 5. So to compare the coefficients of linear combinations, the vectors must be, or must not be, I should say, must not be collinear. In other words, in a line. Okay. And now let's think about the 3D case. So if I'm in the 3D case, I could say, right, I'm going to draw a vector. Let's see how well this works actually in terms of, if I draw a vector and let's draw some other random vector, okay, non-collinear, that defines a kind of plane. This is a bit hard to draw on paper. Hopefully you can kind of visualize it in your mind. If I draw two vectors and extend them forever and think about all the possible points that I can get to by going along a multiple of one of the vectors and a multiple of the other, I would make a plane, right? So for example, if I say you can go any amount of I and then any amount of j, those two vectors allow me to define a plane. And then the third vector has to not be in that same plane. So as long as, you know, all three vectors that I'm comparing coefficients of in their linear combination, if they're all sitting in that same plane, they're not making use of the third dimension, I can't compare coefficients in the way I've done here. I can't declare that A must be 2. Okay. So let's say hypothetically these three little yellow vectors in the same plane, if I said that one's I, that one's j, that one's k, then this equation, I couldn't necessarily deduce that A is 2. Okay. So it's just a note to remind you, most of the time you can compare linear combinations of vectors. The only time you can't in 3D is when the three vectors are in the same plane. If they're non-coplanar, you can compare them. Okay, so fortunately, at this stage, most of the time that's going to be fine. We're going to be talking about IJK. IJK are in fact not non-coplanar. So here we are comparing coefficients, and we're going to find the values of some constants. The constants themselves don't really have any particular meaning. We're just going to find them. So you've got the vector on the left equals the vector on the right. You can convert that into a series of equations. 3 is equal to p plus 2, the j coefficient equals the other j coefficient is minus q, and 120 equals 4pqr. And we know that as a fact. This implies this set of equations because I, j, k are not coplanar. So perhaps, you know, if you're talking about an exam, if it wanted you to justify how did you get from that to this, you might have to just remind, you know, the person you're explaining it to, I, j, k are non-coplanar. And then from that, you're just solving your usual sort of simultaneous equations. So nothing particularly difficult. You've already got p equals 3. Plug that into here. You've got 5 equals minus q. Therefore, q equals minus 5. And then therefore r is equal to, bit of rearranging, you get 120 over 4 times 3 times minus 5 minus 60 minus 2. Okay, but the key thing was being able to go from that to this and justifying why. Okay, and our final example before I give you some questions to do. We've got a cuboid. You know, the picture looks like a cube, it is a cuboid. You're given the vertices O, A, B, C, D, E, F, G. Oh, I'm just going to point out here, remember I said that thing about if you're given vertices, then the shape they describe, those vertices must be in the same order. Obviously that rule, perhaps it's not that obvious, that rule only applies if you're talking about a 2D shape or a shape which has a clear cycle, right? So like if I just draw a square, there's a clear direction to this. I go here and I can loop around the square, you know. Or if I draw some other, you know, funny looking shape like this, say, then the vertices can be given a direction and an order. I can go from here to here to here, and I can follow an order. Whereas here in this shape, it doesn't really make any sense. I can't say I'm here and then I go here and then naturally I follow a specific path. So that's why here the letters, there's no particular order to them. The A and the B and the C and so on, they're just in random places in some sense. So that's when you don't have to worry about it. Okay, but otherwise, yes, you do. Otherwise, the convention is that it's in order. Okay, so I've said that. I've interrupted myself reading the question. The vectors A, B, C are the position vectors of the vertices A, B, and C. Right. Okay, so non-coplanar, right? Let's just make a note of that, by the way. A, B, and C, these vectors are clearly not in the same plane. And we're going to prove that the diagonals O, E, and BG bisect each other. Okay, so that would be O to E is that one, and B to G is that one. It's a bit hard to visualize. And we're going to prove that they bisect. Okay, so these are 3D lines. Well, I mean, all lines are 2D, 1D really, but they're lines in 3D space, and the claim is they intersect, and specifically they bisect. So to say bisect means specifically that this distance here and this distance here are equal, right? And similarly, that distance there and that distance there, they are equal. Okay, so it's not just that they touch each other, they intersect each other, it's also specifically half. Right, so notice there's no actual values going on here. I mean, the closest we've got to a value is we're told that this is little a, little b, and little c. So we're going to have to do this just almost algebraically, right? So we're talking about a general case here, which is quite impressive, right? If we can prove this, then we've proved that for a general case in a cuboid, this is true, that these diagonals bisect. So let's see how we would do this. So I'm going to start by giving a name to this point. Let's assume it does exist. Let's start with the assumption that yes, that point exists, and then derive what would naturally have to be the properties of it, and then see if they conform to what we've been asked to do. So I'm going to call that point H. And then what do we know about H? Let's think about some things. Remember, there's still always this mystery sort of origin out there. Oh, sorry, it's not mystery. In this case, it's here, isn't it? Okay, so then OH, that point, so that's this vector here, if it exists, that's clearly going to be lying on the same line as OE, right? If in fact it's a bisection of that line, okay? I'm not going to say half yet, because that'll be cheating. That's then assuming what I'm trying to prove. So it's some distance along OE. It's going to be some fraction. Let's just call it little r, for instance. I think the textbook does the same. So this is some number less than 1, which tells me where along the blue line this OH lies. I know it's going to be a half, but I need to prove that. So we can't assume it. Okay. And then let's think of another way of defining the position of OH. Another path. What if we did O to B and then B to H? Yeah, we could do that. So let's say another path for OH is, and this will get us extra information, O to B plus B to H. And that's the same thing. If I replace BH with another unknown, it's some distance along this BG line, isn't it? I don't know how far, but it's some distance along there. So let's draw that one. Let's say S times BH. Sorry, not BH, BG. Some distance along that. And then let's think about, can we start turning this into terms of, the A, B, and C vectors? I think we can. So let's talk about this first one and the second one. The first one tells us OH is equal to some multiple of O to E. Now, O to E, how do we get from O to E? This is a cube, right? So I could do A, and then go up here, which is equivalent to C, and then go along here, which is equivalent to B, right? I'm talking about the little letters now. This is little a, that's the same as little c, and that's the same as little b. So, or I could, do another, or I could go little c, little b, little a, it doesn't matter. The point is, if I add up those three little vectors, that's the same thing as going from big O to big E. And in the second case, we've got that, we've got OB, which is little b, plus S, lots of big B to big G. What path is big B to big G? How can I get from there to here? let's come up with something. What about minus b plus c plus a? Yeah, that works. Yeah. So let's call it, let's change the order slightly. So it's effectively a c minus b. Okay, a plus c minus b, same thing. Okay, and then let's just get rid of that and bring this up here. Okay, now let's just equate these. So we've got r lots of a plus r lots of b plus r lots of c, and that's equal to, let's see here, how many lots of b? Oh, let's do how many lots of a. We've got s lots of a. How many lots of b? We've got minus s plus 1. So 1 minus s lot of b, right? So that 1 comes from this b here, and that minus s comes from the fact that I'm multiplying s here by minus b. And then we've got s lots of c. Okay, so comparing coefficients here, what am I getting? I'm getting several results here, or two. Clearly then, because a, b and c are non-coplanar, I can compare coefficients. So r must be the same as s by comparing these two. By comparing the c coefficients, it's the same thing. R must be the same as s. So what about this one? I've got r equals 1 minus s. Okay, r equals 1 minus s. Now, is there a set of values which satisfy both of these equations at the same time? The only ones, if you do your algebraic rearrangement, is r equals s equals a half. That's the only way. Two numbers, they're equal, and yet one minus one of them gives me the other. They're equal to a half. Okay, it's quite a beautiful little proof, actually. And then that's it. If you go back to how you then originally defined OH, it was r lots of O to E, where r is a half. So you've clearly shown it's halfway along. And it's the same for the other case, for BG. We've shown that it's halfway along. Okay, that's it, done. So have a go at this question yourself first. This is quite an interesting one. You're going to be given, you've got 2 points, and you need to find what are the possible positions that the third point could be, which would make OAB isosceles. So you want to think about writing in mathematical notation. How do I define what a triangle is? How do I define an isosceles triangle? What are the special properties about its sides which I can then use to deduce the possible positions of B? Okay, so you want to be thinking about the lengths of distances between vectors. Okay, give that one a go. Let me know if you need help. Pause the video now. Okay, and your 3 possible positions are thus. Okay, and you wouldn't have been able to find those just by drawing the diagram. It's all about the algebraic manipulation of the vectors. Okay, let's look at this one. So you've got a triangle. You're given the points or the vectors from A to B, the vector from B to C, and you need to find the area of the triangle. So you're going to couple what you know about lengths of vectors with, well, I'll give you a hint, but if you don't want it, first have a go at the question. Pause the video now. And if you do want the hint, then for part A, you want to be thinking about either a cosine or sine rule that you can use in conjunction with finding areas of triangles. Okay, cool. All right, I'll let you get on with that question. Pause the video now. Okay, and then there are your answers. Okay, and then this question is introducing an interestingly named shape. This is called a parallelepiped. Parallelepiped, not parallel piped, as I used to think it was called. And the idea is all 6 faces are parallelograms. So it's like you've got a cube or a cuboid, and you've kind of just shifted one side out of alignment with the opposing side, and you've ended up making all of your sides parallelograms. Okay, so this is very similar to the example I did with the proving diagonals bisect each other, except I want you to now effectively try the proof yourself. The logic is very similar, so if you get a bit stuck, you can always go look back and look at what I did in the example. The logic is very similar. And remember, keep in mind A, B and C, again, you know they're non-coplanar, which is why you can do some of the manipulations you do. Okay, good luck with that one. It's a proof question. Try and be rigorous. You can always look back at my previous example if you need some guidance. Okay, pause the video now. Okay, and here is the most succinct way in which the proof is presented. Okay, you may have added a few extra steps or extra bits of working, but these are the key elements of the proof. Okay, and in this case, R and S are just constants that have been introduced. So you may have chosen different constants, that's fine. Okay, and finally, if you've got time, here is a challenge question involving trisection of lines. So remember, to trisect something means that you intersect it at a point which is either a third or 2/3 along the line. See if you can give that one a go. Okay, pause the video now if you haven't already. And the answer, there you go. That's a difficult one. If you've managed to do this one, then you should consider me impressed. Okay, so this is truly a challenge question if you're able to prove this. If you're not, maybe have a go at following through the proof as you can see it here in the textbook. Have the picture in front of you, the diagram. Get that open and try and at the very least follow through the proof, because proving something by yourself is much harder than reading through the proof, but you want to be able to at least do one. So try and read through this proof and understand exactly what's going on. What is this R? What is this X? Understand what all the symbols are, what all the steps are trying to tell you. And if you get stuck, just ask me. Okay, cool.